Hi guys, good morning. Shall we start? Are you ready?
Morning, sir.
Okay, cool. So as we said, last class we completed states of matter. Right. So today we'll be starting with a new chapter. Right. So we'll be starting with equilibrium. Right. Okay. So in any of your schools, this chapter started, guys? In your school, in any of your schools, this chapter started already?
No, sir.
No. Okay. Fine. Cool. So it's a little oh, I said we have to start with thermodynamics, not equilibrium. Okay. I'm sorry, people. I'm really sorry. It's not equilibrium today because we have to understand thermodynamics, then only we can go for equilibrium. I'm sorry. Okay. So we'll be starting with thermodynamics today. Right. Cool. Again, as I already told you, this is one of the most interesting chapters in physical chemistry, right? And my favorite in physical chemistry, right? So, what will you learn in this, right? So, as the name tells you, thermo is heat, dynamics means movement, right? So, we're going to study about heat movement, right, across, I would say, systems. Okay, I'll tell you what systems are, right? So you're going to study about this heat movement, right? And what are all the different parameters. As you're told, you'll be studying about engines. You'll be studying about all spontaneous processes which is happening around the world, right? And yeah, you'll be seeing a lot of stuff in this, a lot of new things you'll be studying. Okay, fine, cool. So when I say heat, so again explaining. So thermo is heat, dynamics is movement, right? So what do you know about heat? Like, what do you think heat is? Tell me. Heat is
Form of
what?
energy.
Yes, heat is a form of energy, right? So there are so many forms of energies we have. Say we have solar energy, we have thermal energy, and obviously thermal energy is what is heat energy, right? And we have kinetic energy, potential energy. So many things are there, right? So many different types of energies are there, right? Uh, but there is one special thing about heat, right? So heat, right? So heat is something which will be able to move from one body to another body. I would say heat can flow from one body to another body if they are kept in contact. Again, obviously, given that the temperature of these two bodies are different, right? So obviously, we know heat moves from a hotter body to a colder body. All these things again. So heat moving from a hotter body to colder body again is defined by laws. Okay, you will see that what are the laws which govern those kind of real life, simple real life situations, right? So all these things you'll be seeing, right? So for us to understand deeply how heat flows, what are all the respective criteria and all that, we have to know certain definitions, small definitions we have to know before moving on to that. Okay, fine. So in order of that, we'll be seeing what is this term system. Okay, fine. So when I say system, system is the particular area, right? Particular volume or whatever your particular space, right? Where I'm going to lay my interest upon, right? Say for example, right? Say for my example, like my entire body, right? My entire body can be a system, right? So when I say my entire body is my system, so the heat flowing into my body, heat flowing out of the body is what those matters, right? So like I don't have to take my entire body as a system. Say sometimes I have to take only my heart as a system, right? So like it's all about how you define it, right? It's all system is not as like say this is what the system. We cannot say that, right? So depending on the problem, depending on the situation, you are going to choose what is your system. Okay, so as I told you, my entire body can be a system, or in my body the particular heart circulatory system can be a system, right? Or a particular cell can be a system. It can be as small as that. Okay, so again in the cell mitochondria can be a system, right? So it is all about how you define it, right? And obviously for you to define it, right, for you to define what the system is, obviously you have to choose what your boundary is it not? right? Only if you choose the boundaries, only then you can say, okay, whatever is inside the boundary is my system, right? And obviously you have to define what is outside my boundary also. So other than the system, whatever is outside the boundary is what is called as my surroundings. Okay, right? So what do you mean by surroundings? Anything other than the system. Say for example, if I take my whole body as my system, anything outside my body, anything, literally anything outside the body, the entire world, entire Milky Way galaxy, everything will come under surroundings. Okay. So first and foremost thing, whenever you're going to do a problem or whenever you're going to realize a situation in thermodynamics, right? The first step you have to do is you have to choose a boundary, right? So that boundary, inside the boundary, whatever you have is what is called as system, and outside the boundary, whatever you have is called as your surroundings. As simple as that, right? So if someone asks you how do you exactly define system, so system is the area or volume or space, whatever it is, in that particular area, you are going to lay your interest upon. You are going to see how in that area only you are going to concentrate on how the heat changes or how much heat changes are going to occur. Is that cool? Right? Okay. Now, depending on certain criteria, right, depending on what is happening, right, I will be able to classify system into 4 types. Okay. I'll be able to classify system into 4 types. What are they? We'll see. Right. So they are classified into 4 types. Right. So first one is what is called as your open system. Next one is what is called as your closed system, and you have isolated systems, and lastly you have something called as adiabatic systems. Okay, open, closed, isolated, and adiabatic. Okay, now it's all very simple, right? It's very simple to understand what are these. Okay, now if you, it is very easier to understand if I look into a real life example, right? Okay, so when I say open system, right? When I say open system, let me take an example of, say, a vessel in which water is there, right? And I'm boiling it. Okay, there is a vessel of water, right? And I'm boiling it. Okay, right. So what do you expect to happen? So definitely, the water would have been initially at 25 degrees Celsius, right? So definitely, you are supplying heat to the system. Again, when I say system, the vessel is my system now. Vessel is the boundary actually. Inside the vessel, I have water. That water is my system. Okay, right. So what is happening here? You are supplying more and more heat energy to the system, right? So obviously the heat content of the system is keeping on increasing, or I don't even want to know whether it's increasing or decreasing, but definitely the amount of heat is changing. Okay, so heat transfer, right? Heat transfer from system to surroundings, or say from surroundings to system, is happening here, right? And not only that, obviously after a point of time when the water starts to boil, right, you'll also see that the amount of water in the vessel has reduced, isn't it? Obviously some amount of water would have gone to vapor phase, correct? So definitely you're going to see some amount of mass also changing, or in better words, I can say that there is going to be mass transfer, right, between system and surroundings, correct? So this is what is an open system. So an open system is one where two things will happen. One is heat transfer between system and surroundings, and second, mass transfer between system and surroundings, right? So heat transfer, yes. Mass transfer, yes, will happen in an open system. Okay, both heat transfer and mass transfer will happen in an open system. As simple as that. Right. I think, guys, there is a glare. 1 second, hold on. Okay. Yeah. So as I told you, both heat transfer and mass transfer will happen in an open system. Okay. Now we'll speak about this closed system. Okay, what do you mean by a closed system? Now I will take the same example, right? Except for one change. What is the change? is I'm not going to leave it open to the atmosphere. I'm just going to put a lid and close it. Okay. Now tell me, what will happen, what will not happen with respect to these two? Heat transfer, mass transfer. What do you think will happen and what do you think will not happen?
Mass transfer won't happen, heat transfer will happen.
Exactly, right? So definitely you are supplying heat. Okay, so definitely the amount of heat will keep on changing inside the system, right? But since you have closed the container, right? So even though some like you can say that some amount of vapors might be there, I'm not denying, right? But that is not going out, right? So definitely there is no mass transfer. The amount of water, say if we had 10 grams of water, there will be 10 grams of water, maybe in liquid phase or in vapor phase, but total would be 10 grams only, isn't it? So in a closed system, I will have heat transfer, yes, but mass transfer, no, nothing. Okay, so no heat transfer, no mass transfer will happen in, sorry, heat transfer will happen, mass transfer will not happen in a closed system. Very simple, right? Now moving on to an isolated system, I think you will be able to guess what is going to happen. So it's very simple. I'm just going to have a tumbler of water kept on table. I'm not doing anything to that. Now what will happen? I'm not doing anything, right? So no mass transfer, no heat transfer, nothing is happening. So that will correspond to an isolated system. Is that okay? Right? So you have an isolated system, no mass transfer, no heat transfer. Very, very simple, right? Okay, now going to this adiabatic system. Again, it's a new name, adiabatic, right? So now what is this? The best example I can give you for an adiabatic system is your thermoflasks, right? So in thermoflasks, what do you think? So why do you use thermoflasks? You tell me.
To conserve heat.
To conserve heat, or like you put it in a real life situation. Why do you use thermoflask?
To make sure the water stays hot for drinking.
Exactly, right? So whatever it is, some liquid tea or coffee or water or whatever it is, the hot water or something, if you pour it into a thermoflask and you close it, right? So it is going to make sure that water stays hot for a longer time, obviously, right? So, but the thing is, in reality, after a point of time, definitely you will see that some amount of heat would have reduced. But in an ideal case, in a perfect situation, so you have to understand that there is no heat transfer happening, is what you have to understand, right? So definitely in an adiabatic system, there will be no heat transfer between system and surroundings. Whatever the heat that particular system has, it is going to have that throughout the process, right? But mass, yes, it can change, right? Again, a real life example, you can pour it, you can obviously change the amount of substance inside the system, right? So in an adiabatic system, heat, no, mass transfer can happen. Okay, mass transfer can happen, right? So these are the different types of system I have: open, closed, isolated, and adiabatic systems. And you must know what is happening in what and what is not happening in all of these. Is that okay? So what is happening is what is happening, what is not happening can be only two. One is about the heat transfer, the other is about the mass transfer. Is that okay? Right. Cool. So that is about the different types of system, right? I understand. We understood what are different types of system. Now what we have to do is, now we understood different types of system. Now we have to study about it, right? So basically, I'll give you an example, right? So you have looked at me, you have understood all these things, right? Now you have to describe me, okay? You have to describe something, right? Say for example, if you want to describe me, you like, I don't know whether you've seen me fully, or seen only till my neck, right? So from whatever you have observed, you can tell that okay, sir has a beard. Uh, okay, if you've seen me fully, you will say that maybe I'm tall, right? I'm little lean, right? So all these things, maybe you can even say that from the classes I have took, maybe so sir is so stupid, right? So all these are the adjectives, all these are the different parameters you will use for describing a person, right? So like this, if you want to describe a system, okay, why do you want to describe a system? Definitely you want to predict how the system will behave on certain conditions, right? Say for example, given that I'm so tall, if there's a situation that I have to take something which is very, I would say in a very, it's a very, how to say, very large heights, right? So obviously you expect me to take it, right? Because I'm a little tall, right? So all these things will be able to predict about me, right? So like that, if you know certain things about the system, right, you will be able to predict how it will behave, right? So now I'm talking about how to describe a system, right? So for describing, like how do you have so many parameters which you use to describe me, right? Like that, there are going to be so many parameters which are going to be used to describe a system, right? So for those things, what and all are the parameters which we already know? I'll tell you what are they, right? So for description of a system, what we have is what is called as your properties of the system, right? So what do you mean by properties? Properties are the variables or properties are the parameters which are used to describe any system, right? Fine. So these properties, right, which use is going to be used to describe a system, right, can be of two types. Okay, so these properties can be of two types. One is what is called as your intensive properties, and the other is what is called as your extensive properties. Okay, intensive properties and extensive properties, right? So what do you mean by this, right? So intensive properties are going to be independent of the amount of substance present in the system. It doesn't care about how much I have. No, these kind of properties are not going to depend upon how much I have in the system, how much mass or how much number of moles. All these things doesn't matter for intensive properties. And obviously, for extensive properties, they are going to be dependent on the amount of substance present in the system, right? Okay. Now, like what and all can be examples of intensive properties? You tell me any examples. Any parameter which is not dependent on amount. Not even one, you remember, you know? Any guesses?
Chemical properties.
Sorry?
Like some chemical properties of some metals or something.
It need not be. Say one thing, I'll tell you. One thing is temperature. Does temperature depend on how much I have? No.
No,
Right? So like this.
Hardness, sir.
What?
Hardness, boiling point.
Boiling point. Okay, temperature. A boiling point is a temperature. So definitely it doesn't depend on the amount. Good. That is one thing. Hardness. Yeah, we can take into account. I will not deny that. Yes. Okay. Any other thing? What about density? Will density depend on the amount? Yeah, tell me.
Sir, taste.
Taste.
Sir, taste.
Oh, taste.
Taste.
Okay. Yeah, accepted. Taste. Yeah, but sometimes, obviously, sometimes I have to eat more to understand the taste, but still, okay, fine, right? So, how about density? What do you think density? Like, is it gonna depend upon the amount? Is it not? Okay, I'll give you a situation, right? Say I have a sugar solution, right? I have a sugar solution with me. Okay, right. Say its density is something, some x gram per ml. Okay, its density is x gram per ml, and say I have, okay, this is some amount is there. Okay, now what I'm going to do is I'm going to transfer it to another vessel, keeping half here and keeping only another half in this. Okay. Now, what do you think will be the density here? Do you understand the situation? I had some amount. Exactly. Okay. So I have some amount of sugar solution, right? And I found that the density was X gram per ml, right? So now what I'm going to do is I'm going to keep only half in this beaker, and I'm going to transfer another half to another beaker. So what do you think? Density here, what will be the value of density here? Or say what will be the value of density there?
So in the second one, density doubles.
Okay. No, it's actually same. It's still going to be X gram per ml only, right? Right. So how do you say it? So density is actually mass by volume, but you don't go by the formula, right? What do you mean by okay? Say I know what is the density of water. What is the density of water? What is the value of density of water? Somebody should know what is the value of density of water. Okay, so assume that you don't know. It is basically 1 gram per ml, right? Density of water is 1 gram per ml, right? So do you think I am going to take a bottle full of water, or if I take a tumbler full of water, do you think that value is going to change? That 1 gram per ml?
You don't, sir.
Exactly, right? So density, maybe you have a very wrong notion about density. You because you know the formula is mass by volume. Both mass and volume are basically amounts, right? So you think that okay, so definitely it is going to be an extensive property, but no, right? It is not going to be actually dependent on the amount, right? So what you have to understand is density is going to be an intensive property. It is not going to change. So how will you decide whether something is an intensive or extensive property? You can do this experiment, right? So you take some amount, like convert into half the amount and check that particular property is changing or not. And if it changes, it's an extensive property. If it doesn't change, it is going to be an intensive property. Okay, so temperature, density, all these things are going to be intensive variables or intensive properties of the system, right? Okay, now going back to what is it? Extensive properties. What and all can be examples? So many examples, right? Number of moles, volume, right? Sometimes even concentration. No, concentration again will come here, right? Okay. What else? Pressure, definitely. The amount of gas, if it changes, the pressure will definitely change, right? Energy, any form of energy for that matter, right? So all these things will definitely be will definitely be dependent on the amount of substance present. Okay, so whenever it's independent of the amount, it's called intensive properties, and whenever it is dependent on the amount, it's called extensive properties of the system, right? So all these properties together are going to be used to describe a system. Okay, so again, what is the use of describing a system? You will be able to predict how the system will behave if for example, if given some amount of heat. Oh yeah, heat, again I told you energy, definitely heat is also an extensive property. Okay, fine. Anyways, so it will be used to predict how the system will behave on certain situations, right? If you know all these variables or if you know all these properties, right? Now, right, thermodynamics as a tool is very useful, right? Now, why is it so very useful? Is because the amount of information it needs is very less, okay? But the amount of information it is going to give you by taking those informations is going to be enormous. Okay, again, I repeat, right? So thermodynamics as a tool is very useful, right? Why is it so useful? Is because the amount of information it takes in is very less, but with those information, how much information it is going to give you is enormous, right? Now, how will I prove it to you? This is how I prove it, right? So if at all you want to know anything and everything about the system, That means if you want to go for 100% description, what do you mean by 100% description? You are going to know anything and everything about the system. There is nothing you will not know about the system. For this, right? For this particular thing, I don't require much things. Okay, I really don't require much things. I require only 3 things which I have to know about the system. And if I know these three things, I know literally everything about the system. Right? So what and all are these 3 things which are required? Very, very simple. So the thing is, you need to know 2 intensive properties of the system. Right? Any 2 intensive property, you need to know about the system. That is 2 of the things. And one more is about the number of moles of the system. Okay, number of moles of the particular compound or whatever it is inside the system. Okay, so if these 3 things you know, right? If you know these 3 things, yes, definitely you know anything and everything about the system, right? Say the intensive properties can be, say, temperature, right? Okay, but the thing is, right? The thing is, you will not be always given intensive properties, right? For example, they might give you volume, they might give you whatever, something else, right? So at that time, what will you do, right? There is a way by which you will be able to convert an intensive property, an extensive property into an intensive property. Okay, there is a way by which you will be able to convert an extensive property into an intensive property and then use this for this 100% description. Okay, so what is the way is that any extensive property, right? Any extensive property, if you divide it by the number of moles, you are going to get an intensive property, right? Any extensive property divided by the number of moles, right, will give you the intensive property. Now, why am I dividing this? Why am I dividing by number of moles? Now I'm making sure that the number of, like the amount which I'm speaking about, already the extensive properties are going to depend upon the amount. I agree, right? Now what I'm doing, by dividing by the number of moles, I'm making sure that the amount is constant. Everything is going to become per mole. For 1 mole, what is the extensive property? And obviously, if I'm going to decide what is the amount, it is not going to depend upon the amount. So it is going to become an intensive property. For example, you would have seen all the energies. Generally, we say energy in terms of what? Joules or kilojoules is what we use. That is the SI unit of energy, right? But in so many cases, not only here, like throughout this chapter, right, we'll be seeing joule per mole is what we use. Okay, so many times kilojoules per mole, kilocalories per mole, like that only we will use. And what is the reason? This is the reason, because energy is an extensive property, right? If I divide it by the number of moles, if I make it per mole, then it becomes an intensive property. Okay, same way I can do with volume also. Say volume, I know is an extensive property. If I divide volume by the number of moles, you are going to get something called as V bar. V bar is nothing but molar volume. What do you mean by molar volume? Volume of 1 mole of the substance, right? Volume per mole. That's what I can say, right? So like this, you will be able to convert any extensive property into an intensive property. How? By dividing the extensive property by number of moles. Is that okay? Right? Cool. So that is about how you describe a system with this extensive and intensive properties and all that, right? So moving on. Right. So moving on, we'll speak about this heat. Okay. So obviously this chapter is all the things about heat. So we need to know certain things about heat. Okay. Fine. Right. So we already know that heat and temperature are some way related. Is it not? Right. Why? Obviously, if I'm going to supply more amount of heat, you see that the temperature is changing. Correct. Right. Say Obviously, if I'm going to make sure that if I keep on really decreasing the temperature, obviously I know the amount of heat inside the system changes, right? So you can have actually a rough understanding that heat and temperature are actually related to each other somehow. Somehow they are related to each other, right? So we are going to see what is the relationship, right? What is the relationship which makes, what is the relationship which connects my heat and temperature? We are going to look into it. Okay, right. So, and one more thing is certain substances, right? Certain substances with a small amount of heat you give, right? With a small amount of heat you give, you are going to see an enormous change in temperature, right? Say I give 10 joules to a substance X and same 10 joules of energy or 10 joules of heat to substance Y, they might not have the same temperature change. Say, for example, in substance X, I would have had some 2 degrees Celsius rise because of the 10 joules of heat given, right? But you might not see the same 2 degrees. It might be 3 degrees, or it might be even 1 degree rise temperature in substance Y, right? So why all this is happening? All these things we'll be seeing now. Okay, right. So please understand, people. I already know the okay. Now heat, it is denoted by the letter Q, right? Heat is denoted by the letter Q. This notation will be using throughout this chapter, right? Heat is denoted by the letter Q. Okay, so I would have written there out. Maybe if you're seeing extensive properties, I wrote, when I said heat, I would have written Q, right? This is just a representation, right? So Q means heat. That's a representation, right? Okay, so we already know this Q is definitely directly proportional to the change in temperature. Is it not? More and more amount of heat you give to the system, more and more will be the change in temperature. That we already understand, right? So from this itself, I'll be able to give you an equation, right? So since Q is directly proportional to delta T, that is change in temperature, right? So if I remove the proportionality sign, right, and I can write it as C del T, some constant C into del T. Okay. Now this C is a very, very, very important constant. It's not some random proportionality constant, right? So this particular C, that which I've written here, is going to depend on what kind of substance I have. It is going to be different for different compounds, different materials. It is going to be different for almost everything, right? So what is this C, right? So this C is what is called as this heat capacity, right? This what is it? C is what is called as your heat capacity. Okay, so we will be speaking in depth about this heat capacity, but what you have to understand is, people, right? This, I told you, Q is an extensive property, right? That means it depends on the amount of substance. Okay, so there can be two equations by which we'll be able to write. So one is I can write in terms of mass. Say this much amount of substance mass I have. So one equation is Q is equal to mc del T, where m is the mass, right? Or I can write in terms of number of moles also, right? So I can write it as nc del T, where n is the number of moles. Okay, but the C value which you use here in both these different cases will be different, right? So in this case, it is going to be called as mass heat capacity, right? It is going to be called as mass heat capacity because you're using mass in the equation, right? And in this case, the C you use is what is called as molar heat capacity because you're using moles, and the values will definitely be different. Okay, but the essence of the whole equation is same, right? Q is an extensive property which depends on the amount. What amount you use, whether you're using number of moles or whether you're using mass, depending on that, the heat capacity value changes, the name also changes. And if you use mass, it is going to be called as mass heat capacity, right? And obviously, if you're going to use number of moles, it is going to be called as molar heat capacity. Okay, fine. So we will try to give a proper definition, right? We'll try to give a proper definition for this heat capacities. Okay, please take down, right? So please understand, people, you are going to make sure you can define both of them, right? But if I give you one of the definitions, it is understood. Like the other one is going to be very, very easy, like how you are going to define it. Okay, now how am I going to define it is going to depend on this. So please understand, say for example, if I take this mass heat capacity, Q is equal to mc del T. Okay, so if I put 1 gram of a substance, right, if I take only 1 gram of that particular substance, right, so I give some amount of heat to the system. Okay, I give some amount of Q, some amount of heat to the system, right, such that there is 1 degree Celsius rise in temperature. Okay, again I repeat, I am going to give some amount of heat to the system, right, making again what there are some amount of heat to the system of 1 gram. There is 1 gram inside the system of the particular molecule or a gas, whatever it is, right? So I'm going to give some amount of heat to the system, right, making sure that the increase in temperature was 1 degree Celsius. That means what? Delta T is basically going to be 1 degree Celsius rise. Okay, right. So now obviously what will happen if this is going to happen? What can I say? If it is 1 gram and this is also change in temperature is 1 degree Celsius, I can say that Q will be equal to C, isn't it? And this is exactly how we are going to define it. Please take down mass heat capacity. The definition of mass heat capacity. Please take down. It is the amount of heat required. It is the amount of heat required to raise the temperature. It is the amount of heat required. It is the amount of heat required to raise the temperature of 1 gram of a substance, right? 1 gram of a substance by 1 degree Celsius or 1 Kelvin, right? By 1 degree Celsius or 1 Kelvin. Again, I repeat the entire statement, right? It is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. Whatever I told you exactly, we wrote it in words.
Sir, the following definition is for what, sir?
Mass heat capacity. We're talking about mass heat capacity. That's when I told you, right? When mass is 1 gram, when change in temperature is 1 degree Celsius, the amount of heat and C will be equal, right? So that's how we're going to define this mass heat capacity. Okay, so mass heat capacity is the amount of heat energy required to raise the temperature of 1 gram of substance by 1 degree Celsius or 1 Kelvin. Is that okay? Any doubts, any questions, people, from this? Hope you understood, right? Nothing. Yeah.
No doubts.
Okay, cool. Right. So what will be the unit of this mass heat capacity? You tell me. What will be the unit of mass heat capacity?
Sir, kilometer square per
Kilometer.
kilogram.
Kilogram. Okay, kilogram will be there. Okay.
Sir, kilogram square per
Why
per
kilogram
per
square?
Kelvin.
Wait. Why kilogram square?
So sorry, sir. Kilogram per second per Kelvin.
Per second. Sir, what is happening? Am I talking about anything moving? Second?
Kilogram per Kelvin, sir.
Kilogram per Kelvin. No. Any other answers? Kilogram is there, Kelvin is there, but not in that order. There is one more thing which is missing. So go by the definition. What is it? It is the amount of heat. That means what? What should be there?
Temperature should be.
Joule.
Sir,
Correct.
joule
Joule.
per Kelvin.
You
Joule per
said?
Kelvin.
Joule per
Exactly.
kilogram Kelvin.
Correct. Joule per Kelvin per kilogram. That's how it should be. Right? For 1 gram of a substance, for 1 degree Celsius rise, what is the amount of heat energy required? So very simple. So for mass heat capacity, for mass heat capacity, the unit is joule per Kelvin per kilogram. That's the unit of mass heat capacity. Okay, now how will I define this molar heat capacity? Very, very simple. Instead of in the definition of mass heat capacity, if I just change 1 gram to 1 mole, then it becomes molar heat capacity. If you want, you can take it again. It is the amount of heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius or 1 Kelvin. Right? Like what I'm telling is, from the mass heat capacity definition, if you just take out 1 gram and you put 1 mole, then it becomes your molar heat capacity. Now tell me, what will be the unit of molar heat capacity? What will be the unit of molar heat capacity?
Sir, joule per Kelvin.
Then that's it.
Mole.
That's it, right? So now it's very simple, right? Here you saw joule per Kelvin per kg because you're using mass. Now in this case, I'm using mole. So only difference would be joule per Kelvin per mole will be the unit of molar heat capacity. Is that okay? Right? Joule per Kelvin per mole for molar heat capacity. Joule per Kelvin per kilogram will be the unit of mass heat capacity. Is that okay? Any doubts?
No, sir.
Okay, cool. Right. So we understood what is this heat capacity, and we have defined 2 different heat capacities also, right? Okay, we'll move on. So the thing is, people, so yes, we understood what is this heat capacity. We defined all the heat capacities, all that we have done, right? But still, what to say? The conditions on which at which I do the process, that is the process of giving some amount of heat, right? How am I, at what conditions I do the process matters. Okay, so you don't have to worry about so many conditions. There are going to be only 2 conditions. Either you can supply or remove heat at constant volume conditions, that is the volume is not changing, or you're going to do it in a closed vessel, something like that, right? Now definitely at that time the temperature change, for example, how do I put it, say assume this conditions, okay, say I'm going to boil water. Okay, now I'm going to boil water in an open vessel, that is the top is open to the atmosphere. Okay, say I give some 10 let me draw it. Say I'm going to give, say, 10 joules of heat to this. Okay, now the same thing, I have same amount of water. Say this is some 10 grams of water is there. Same 10 grams of water I take here, but in a closed system. Same 10 joules of heat energy I give here. Okay, now I don't want to know like exact details, but do you think the temperature increase, will it be same or different in both these cases? The temperature increase, right? Will it be same or different in both these cases? What do you expect?
It will remain the same number.
Almost it is going to remain same, but definitely it is not going to be exactly same, right? Say it might be some For 10 joules of heat, say I get like some 1.5 degrees Celsius rise in this case. Maybe in this case, it might be around 1.3 degrees Celsius rise, but still, even though they're almost same, they are not exactly same, right? So obviously what you see here, this is my constant volume conditions. This is my constant volume. And in this case, it is going to be constant pressure conditions. Only atmospheric pressure is acting. No other pressure is acting. Constant pressure, right? So these two conditions, that is whether I'm doing the process in a constant constant pressure conditions, or whether I'm doing the process in constant volume condition matters. Maybe in this case, you might be seeing only very small differences between these two, but there are cases where you will see enormous differences, right? So much difference you will see in the temperature rise. Is that okay? Right? So how you are going to do the process, what conditions you are going to do the process, whether are you going to do it at constant temperatures, constant pressure, or whether you're going to do it at constant volume matters. Okay, so obviously what you see here, so in this case, for assume that how do I put it, say for delta T to be 1 degree Celsius rise in both of them. Okay, say in this case, for 1 degree at 1 degree Celsius rise, I gave 5 joules of heat, right? So now say in this case, for 1 degree Celsius rise, I gave like 4.5 joules of heat. Okay, in both the cases, I'm going to see, now in this case is different from what we saw. Last time what I did, I give same amount of heat energy and I saw how much temperature is changing. Now what I'm seeing, for 1 degree Celsius rise in both of them, how much heat energy is required is what I'm seeing, right? So in the what I found out is for 1 degree Celsius rise here, I require 5 joules of energy, and for 1 degree Celsius rise here, I have 4.5 joules of energy required, right? So now this is how I define my heat capacity, isn't it? Right? For 1 degree Celsius rise, how much is the amount of heat energy which is required, right? So depending on how I do the process, what do you see? My heat capacity value is also changing. Is it not? For 1 degree Celsius rise here, I require 5 joules. For 1 degree Celsius rise in this condition, same amount, I require 4.5 joules. That means what? The heat capacity value in this case and the heat capacity value in that case is actually different. Okay, so for these reasons, whether depending on how I'm going to do the process, the heat capacity value is also of two types. Like two types we already saw. One is mass heat capacity, another is number of moles. That is different. That is just based on what units you are taking, right? But in this case, it is going to depend on how I do the process. Okay, so based on that, I'm going to get two different heat capacity values, right? So one is what is called as CV, the other one is what is called as CP. Okay, so what do you mean by CP? What do you mean by CV? CV is heat capacity at constant volume conditions, right? So if in this condition, right? So if I have I'm going to do the process at constant volume conditions. Okay, that is what is called as CV. That value of heat capacity is what is called as CV, represented by CV. Okay, same way, CP is heat capacity at constant pressure, right? So when I'm going to do when I'm doing the process at constant pressure conditions, whatever the value of the heat capacity, it is going to be called as CP, heat capacity at constant volume. Okay, and definitely I will tell you what will be the relationship between these two. Also, we will derive the relationship. I can tell you the value right now. CP minus CV is basically equal to the universal gas constant R. Okay, so don't worry. Like now you don't have to know it. Just I'm telling the difference between CP and CV is only going to be R. R value we know is universal gas constant. Okay, fine. So what is the time? It's almost 8, right? So we'll stop with this for today, right? We'll speak about this heat capacity in a very detailed sense in the next class, and then we'll see so many other exciting things. Okay, so you don't have to remember this for now. You will anyways derive it. You will derive this in physics also. This is called Mayer's relationship. This is called Mayer's relationship. Anyways, you don't have to know it now. We will be seeing it at the middle of the chapter somewhere. We'll be seeing the derivation for this. Don't worry. But even if, I don't think you need the derivation, but still we'll derive it, right? So today we understood what is heat, right? What are all this? What do you mean by system? What do you mean by surroundings? Boundary, different types of system: open, closed, adiabatic, isolated, right? Then you went on to see how do you describe a system with the help of these properties, so-called properties. Again, they were of two types: intensive and extensive. Intensive depends on the amount. Sorry, independent of the amount. Extensive depends on the amount. Then I told you, for you to go for 100% description, for you to know anything and everything about the system, you just need three things. You just require two intensive properties and the number of moles. And I told you, every time intensive properties will not be given to you, but you can convert extensive property to an intensive property by dividing by the number of moles, right? Then we went on to see how this heat and change in temperature are connected, right? And we told that the proportionality constant there is what is called as heat capacity, right? And I told you Q, that is heat, is is an extensive variable. That means it is going to depend upon the amount. So based on whether you're going to take mass or whether you're going to take number of moles, I have two different types of heat capacities, where that is my mass heat capacity and molar heat capacity, and we have defined all of them, right? And then we went on to see the heat capacity value is also depend on how you do the process, whether you're going to do the process at constant pressure conditions or whether you're going to do the process at constant volume conditions. Based on that, I have Cp and Cv. Cp is heat capacity at constant pressure. Cv is heat capacity at constant volume. These are all the things which we learned today, right? And we don't we are just entering the chapter, right? There are so many other exciting things to come, right? So people, any questions from all
I have a
this?
doubt.
Yeah.
So the Cv and Cp the value will change depending on the heat capacity at like mass heat capacity and molar heat capacity. It has.
Yeah, so this is, you see, this can be molar heat capacity at constant volume or mass heat capacity at constant volume. Again, this can be either mass or it depends on what you want to use. If it is going to be a liquid, generally, like if it is going to be unknown compound, for example, you don't know what is there in the system, right? At that time, you prefer to use mass because you might not know what is the molecular mass of the system. But if it is a known gas, say for example, oxygen gas is there, you definitely know this is the amount, and definitely you can speak in terms of number of moles. So it depends. And there is no restriction which you have to use. Okay, and is that your question?
Yes, sir.
Okay, so there is no restriction, Kanna. This can be mass or number of moles, or again, this can be mass or number of moles. That doesn't matter. But how we are doing the process, whether it's constant at constant volume or whether it's at constant pressure, that is more important than those things. That is whether you're going to use mass or number of moles.
Okay, sir.
Is that okay? Right. Any other question, people? Okay. So I hope there are no questions. So fine. So I will be seeing day after tomorrow. We'll be continuing this. Until then, thank you. Bye bye.
Thank you.
Thank you.
Thank you, sir.
Thank you.